Analyze geoscience data to make the claim that one change to Earth's surface can create feedbacks that cause changes to other Earth systems. Okay. Many gases make up Earth's atmosphere, including nitrogen, blah, 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 like the windows in a greenhouse. I guess, are we going to be doing a simulation? Okay, so then I'll bring up a copy so that this is ATA number 7. That way, it might be easier, I think. So let's take a look. All right, let's go here. Let's go to the board here. Okay, many gases make up Earth's atmosphere, including nitrogen, oxygen, blah, blah, blah. And carbon dioxide, water vapor, and methane have the ability to act like an insulator for the planet. Check for, use the reading above, answer the following questions. Okay, so that'll be easy enough. We'll do that. Then here, climate data graphs. Examine each graph provided and then answer the questions. Graph 1 shows the level of carbon dioxide that was in the atmosphere in prehistoric times. Scientists retrieved this data from air bubbles trapped in ancient ice in Vostok, Antarctica. I see almost a little bit of a cycle. It starts and then comes down, then goes up, and then comes down, and then goes up, and then comes down, goes up, and then comes down, goes up. What do we think is going to happen next? Go down. So we'll see, but that's, when you look at a graph, sometimes, Lorraine, it's important to look not just at the data, but to look at what you see generally. All right. And there's some questions there. And then here's another one. This is carbon dioxide. This is strictly going up. Lots of little cycles, up, down, up, down, up, down, up, down, up, down, up, down. Not a big range. It doesn't go as big as the other graph did. We don't see lots of things going up and down the same way. But we see that it's going up generally. And then about how many parts per million of carbon were in the atmosphere compare and contrast. Surface temperature anomalies. This isn't as much we see some cycles and it's like the peaks get higher, but it's not just the same. Let's see. Kind of like down and then up, back up. The bottoms still seem to be the same when we go across. So we'll look at that a little more closely. And then describe what happened to Earth's temperature. Yearly surface temperature anomalies. So Lorena, an anomaly is something that doesn't fit into a pattern. Anomaly. It's an important word. So let's look up anomaly so we know exactly what we're talking about. Here's the word anomalies. A-N-O-M-A-L-I-E-S. That's a plural. One anomaly is spelled A-N-O-M-A-L-Y. Anomaly. Let's go to the definition. Something different, abnormal, peculiar, or not easily classified. It doesn't have to be bad. Something different or not easily classified, something anomalous. They regarded the test results as an anomaly. So that's kind of the idea, something that doesn't fit into the pattern that we're thinking of. So something that doesn't fit perfectly is an anomaly. And if you have a group of them, you have a lot of things that don't fit into a category. You cannot classify them easily and describe them. So that's what these are, yearly surface temperature anomalies. And I guess it's the difference from the average. If the average temperature is supposed to be some number, then when there's a spike, these are spikes here, that's an anomaly. And I guess this means down lower. If the average temperature was, I'll pick a number, 60 degrees Fahrenheit, then over a 10-year period, there was a period, there's a time when the temperature was a little bit colder by a half a degree in 10 years. And then here there's a couple of anomalies. And then here's one, and it's colder. And then look here, if we get to 1930, we start to go up in the anomalies, hotter than average, half a degree higher than the average. And then it comes down and then it stays. And now the trend is to remain above, not to be at the average of 60 degrees, because this is not plotting 60 degrees, it's plotting the difference from 60 degrees, warmer or colder. And the spikes in all of this are anomalies, differences from the expected average. So there's where the average would be, where it says 0, looking across. And now you can see starting around 1930, we very rarely go colder by a half a degree. And now starting in 1975 or so, right about here, we stay always warmer and the anomalies get larger. We're now up here at regularly 1 degree above the average. So, and this is a government, climate.gov, so that's government data that we've been, that's all those people who go out and record temperatures and we put it all together. They've been doing it since at least 1880. So that's pretty good data. That tells us that there is warming, yearly surface temperature, the surface of the Earth. And do you remember how we learned about the surface of the Earth getting warm from the sun radiation, right? Remember the sunlight photons come to the ground, they release infrared photons, and then sometimes they get trapped, and then that makes the temperature higher. That's what's happening right here. This is a picture of the last 50 years of the temperature getting warmer. Okay, so that's what that's showing us. And we can go through, a lot of these questions look pretty easy. Greenland ice mass loss. When you lose something, we can track when you lose something. And what we're talking about is the ice on Greenland. And that's a big deal. Do you know where Greenland is, Lorena?
No.
All right, I'm going to show you right now. All right, so here we go. Where is Greenland? Greenland is off of the coast of Canada. So, oh, this is pretty good. BBC News, Greenland. So here is Canada, and here is Canada and the United States. And this is very far north. There, in this little picture here in the corner, do you see this picture in the corner? Here's South America, North America, and then Canada is up here, and that's what we're looking at, and that's Greenland. Here's Canada, and it's cold. Up here, we're much closer to the North Pole, and Greenland is here, and Iceland is here. Iceland is a smaller island in the North Atlantic. It's very cold, and here's Greenland, and it has been covered with ice, an ice sheet. Like you make your bed, you have a sheet. This is a sheet of ice that's over the most or a lot of Greenland. But they're losing the ice. They're losing the ice because of the temperatures that we saw in here higher up. Where is that? Right here. Here, we're looking at yearly surface temperature. That's for the whole Earth, and including Greenland. So yearly surface temperature has been going up, 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 above average. Well, if the temperature is warmer everywhere, ice doesn't do very well. Ice starts to melt. And then as the ice melts, it's like a mirror. It doesn't send back a lot of the sun's radiation. If we absorb the sun's radiation, then more of the heat stays on the Earth. And that's what's happening here. And that melts ice. So if we look at Greenland right here, and we talk about how much ice has gone away, that's the loss. We see this 1992. Let's go back and look at 1992 right here. Here's about 1992. Look at that. What do you see here, Lorena? Do you see the map I'm looking at? Yes? Yearly surface temperature anomalies. Do you see this? And you see where my little crosshair cursor is?
Mm-hmm.
Okay, good. I'm glad, because I wasn't sure if with the board. Here is 1992. Hotter, 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 hotter. More hot. More loss of ice. Losing ice, losing more ice, losing more ice, losing lots of ice, losing way too much. How much? These are in GTs. I guess that's tons, is what I'm guessing. Greenland ice mass, cumulative ice mass loss, uncertainty range. Uncertainty means they're not sure, but this is what it looks like. This thick line right here. Whatever the unit is, tons of ice. Where does it go? If we're in Greenland and this ice melts, where does it go? It goes in the water. It just runs off. It turns into water and it runs down through the streams and into the ocean. And if you lose millions of tons of ice, it turns into millions of tons of water. It goes in the ocean, a little bit of going up. How much? Well, we don't have to pay too much attention to it right now. Let's see any other pictures. Doesn't look. No, but see there's big pieces of ice. This thing, look, these are houses right here. See this picture? It's a big piece of ice. It probably, I'm assuming, I don't know, probably broke off from the edge of Greenland. Now it's out in the ocean. Bye-bye. Tons and tons. That's probably as bigger than in one of those ships, a container ship. Incredible. All right, so that's enough of that. So now we're back here. That's what's happening with this graph. And then, aha! I said, ice mass loss, where does it go? It goes into the ocean. All right, and this is from 1992 to 2012, 1992. So we go back down here, and now we look at sea level changes. Sea level change is the sea going down all across the world, all of the water, because it's not higher in one ocean than the other, because all the ocean, the water is allowed to circulate. So it's all the same height. Maybe in lakes, they could be lower or higher, but in the ocean, or we just call it the sea, all of it. Okay, the sea level change. This is from NASA, so this is good data. This goes all the way back to 1880. We don't care about 1880 right now, because what we care about is 1992. That's what we can compare from 1992 to 2012 for the ice loss, and up here from 1992, which is just over here, that the heat increase. We would look right from here and just look at this piece right here. And so now we're going to go down. We have another bunch of data from 1880 about the ocean, the sea level changes. Well, we don't really want to look all the way back here because we really want to look at around 1992. Well, here's 2000. So halfway between 1980 and 2000 is going to be 1990. So I look up here and I look up, and what do I see? I see something way above the rest. So what is this? Sea level change in millimeters. How big is a millimeter? Tiny. Millimeters are tiny. This is a meter. Look at my picture. Don't look at the screen for a second. Let's stop the share. Okay. This is a meter stick. And in a meter stick, those are centimeters. There are 1,000 millimeters. I don't know if this will work if I come up close. Yeah, it does. We're looking at the bottom stuff down here. Here. The little tiny lines. Does that work? The little tiny lines are millimeters. The long lines, the 1, the 2, those are centimeters. Each one has 10. Let's see, 1, 2, 3, yeah, 10 millimeters for every centimeter, and there are 100 centimeters in a meter stick. It goes up to right there, 100. And so that's 1,000 millimeters. This is 1,000 millimeters. So now if we go back here, go back to the share. And now we're looking here, and the sea level change in millimeters. How much has the sea changed since about 1990? All right, we're going to say it's like at 150, and now 2020, it looks like, let's pretend that that's around 2020. All right, so we're saying 1990, about a little more than 150, 160 millimeters. And then around now, 2 years ago, it's at 240, 160, 240. What's 240 minus 160? It's 80 millimeters. How much is that? It's right here. Let's do it this way. There you go. See, I'm pointing to the 8 because there's 80 millimeters. The ocean has gone up a little more than 3 inches. See, these are inches on the right. The sea has gone up a little more than 3 inches in 30 years. Where's the pen? There it is. Okay. 3 inches around the world. 3 inches doesn't sound like a lot, but okay, so that's from 1990 to 2020, let's say, 3 inches. All right, how about 2050? When's 2050? 30 years from now. Let's say it's the same trend. Might be larger. It would be 3 more inches. And it would be here by 2050. Okay. Now I'll be gone because I'll be 100 in 2056. So maybe I'll be around because my dad is 94. And then, you know, another 30 years. Now, that's a lot. 9 inches. but we're starting to see the effects on the coasts where people have built houses, and 3 inches of sea level change already, they weren't expecting it. And I don't know if 3 inches just means as an average in some parts it's higher, but you definitely don't want to be below sea level because the sea level has gone up. New Orleans is below sea level. Venice, Italy, has its own problems because it's sinking all by itself. And so that's a big change. All right, so let's go back here. It's enough of that. But we needed to do all this to understand what we're looking at. Okay, so there's the sea level changes. And then this is your thing, what you have to do. Claim, evidence, and reasoning. Do carbon dioxide levels in the atmosphere and the Earth's temperature appear to be related? Yes. All right. So now we know what we're looking at. This is a lot of stuff to do. So let's get going. All right. Check for using the reading above, answer the following questions. What are greenhouse gases? Okay. All right. Like the windows in a greenhouse, I'm reading right here. Like the windows in a greenhouse, these greenhouse gases. What are the greenhouse gases? Nitrogen, oxygen. Here's nitrogen, oxygen, water vapor, argon, methane. Remember methane? That's like cow poop. And it was like one of the things that trapped the most infrared photons. Methane, carbon dioxide, and nitrogen were the 3 that trapped the most infrared photons when we did the experiment. Remember, we had to come up and trace and make an atmosphere. Do you remember that, Lorena?
Yeah.
Yeah. And what we found was nitrogen, methane, and carbon dioxide trapped the most. So we don't really want a lot of that in the atmosphere, but they are there. And then including beyond nitrogen, you have oxygen, so we can breathe. Water vapor when it's humid or wet or when it rains. Argon, I forget what argon is. It's another element. I can't remember much about it, but that's about it. So carbon dioxide, water vapor, and methane have the ability to act like an insulator for the planet, trapping infrared photons. Like the windows in a greenhouse, these greenhouse gases, so these are all called greenhouse gases. Nitrogen, oxygen, water vapor, argon, methane, and carbon dioxide are all greenhouse gases. These greenhouse gases trap energy from the sun as heat in our atmosphere. More red photons. Remember all those photons. Okay. Without their role in this greenhouse effect, Earth would be quite cold. Yes, it would be very, very cold because all those, the sunlight photons would come down and a lot of it would bounce back. And we would not stay in the atmosphere. It would not be warm, it would be cold. Because of greenhouse gases, the surface of our planet averages around 59 degrees. Okay, so that was not too bad. I guessed 60 degrees, making it the perfect place for life. Ah, so wonderful. Since about 1850, however, human activities have been releasing extra greenhouse gases into the air, particularly methane, methane and carbon dioxide, we know that they can do a lot. Extra trapping infrared photons. Extra methane enters the atmosphere from livestock. It's cow poop, steer poop. We feed the cows in order to get the milk and then to eat the meat. And there's all the poop lying around, being methane, trapping infrared photons. Extra carbon dioxide enters the atmosphere by burning fossil fuels gasoline, cars, right? Airplanes, ships, anything that burns gasoline or diesel or coal. All of those are fossil fuels. They're old stuff. And we dig it up and we process it. We turn it into gasoline. Okay, so carbon dioxide enters the atmosphere by burning fossil fuels such as gasoline and coal for transportation, for our cars, the trains, ships, all that stuff. And that's where we get electricity. It's one of the main ways we get electricity. We can also get electricity from solar panels and the wind, but not as much as we get from coal, and hydroelectric is important. Waterfalls. You make water goes down all by itself and it spins something, and we can make a dynamo. Lorena, did you ever watch the movie The Boy Who Harnessed the Wind?
Mm-hmm.
And he had a little dynamo. Remember, he wanted the dynamo from the teacher with the bicycle, and it would spin and it would make electricity. That's how hydroelectric, spin, enormous dynamos, giant dynamos make electricity. But coal is still important, and nuclear, all these other things. But nuclear doesn't, I don't think nuclear produces carbon dioxide. Scientists think that this increase in greenhouse gases has slowly caused a rise in average temperatures across the Earth. Well, we just saw that, right? In further down, if we just looked at all the charts and we said, yes, you're right, we saw that. Scientists think that this increase in greenhouse gases has slowly caused a rise in average temperatures across the Earth. Well, we saw that when we started looking at like 1992. I think that's what we wrote, 1970 also. But we really wanted to focus on 1992 because the other graphs talk about stuff from 1992. Many scientists agree that the greenhouse gas contributing the most of the rise in average temperature is carbon dioxide. Gasoline burning, coal burning, diesel burning, all of that. Everybody, you know, not everybody has a car, but the more people, the more cars. The more cars, the more carbon dioxide. That's why there's all these ideas of trying to become electric. And the car manufacturers, some of them are pledging to be all electric by 2050, when the ocean will rise another 3 inches, because it's already risen 3 inches from 1990 to 2020. Today, you will analyze several graphs to get an insight into why scientists are concerned about the extra carbon dioxide and increasing temperatures. So what we did at the start of this, Lorena, is we went down and we looked at the charts. What you and I have just done is we have sort of analyzed several graphs already so that you'll be able to do stuff. Using the reading above, answer the following questions. What are greenhouse gases? Greenhouse gases are nitrogen, oxygen, water vapor, argon, methane, and carbon dioxide. That's what goes right here. That's the first part. How could extra carbon dioxide be responsible for increasing temperatures on Earth? Let's see the sentence. All right, this sentence right here, scientists think that this increase in greenhouse gases, has slowly caused a rise in the average temperatures across the Earth. That's what would go here. But you could also write that more carbon dioxide in the atmosphere traps more infrared photons. You did that science experiment, and this is a science This is your science or your physics class. So you could be talking about that also. You could just write that. Carbon dioxide, you know, when we did some tests with carbon dioxide in the atmosphere, we saw it trapped more infrared photons, and that leads to higher heat. So you are a scientist too when you've done that. That's the answer there. Here's a picture we saw about carbon dioxide cycles, but this is 400,000 years ago. Who cares? We don't want 100,000 years ago. We want now, and we're in that cycle of carbon dioxide going up, and it's whatever the level is. I don't think this graph is as important as the other stuff. What time frame does this graph include? 400,000 years ago to the present. That's what goes here. 400,000 years before the present. You can just write this line right here. It goes there. All right. So we'll check all of this stuff some more. What I'm doing is I'm trying to go through it with you so you can have an idea in your head. Plus, Lorena, I will make this recording available to you later today. This class ends in a couple of minutes. I'm going to go through this, but then the recording of what we're just doing now will be available for you to replay. So all the answers that I'm telling you now, you'll be able to rewind. All right. What time frame does this graph include? 400,000 years to the present. Describe what happened to the overall level of carbon dioxide over this period of time. The overall level of carbon dioxide over this period of time went through various cycles of rising and then falling, then rising and falling, rising and falling, rising and then falling. Okay. About what is the highest level of parts per million of carbon dioxide in the air in the 400,000 years before modern time? In other words, what level was never exceeded? Never exceeded was 300. What are these? Is this parts per million? Atmospheric carbon dioxide levels, 300, and I don't know what the units are. Parts per million, right here, it says parts per million. Never above 300 parts per million. Okay, and there's this graph, right? Carbon dioxide. Uh-oh, there it is, parts per million. Take a look at this. Here, it never went above 300 parts per million. Whatever the present is, I mean, it's not really the present right now, but here, look at this. This is carbon dioxide parts per million. It's the same scale. It was never above 300, which is down here at the bottom. Never before above 300 parts per million in 400,000 years. Now, since 1960, so the last 60 years, it has always been above 300 parts per million. All of these numbers are above 300 parts per million. And now we're at 400 parts per million. Ay, ay, ay. What time frame does this graph include? This graph includes 60 years of data. It appears to be approximately 60 years. Mm-hmm. All right. Did the Industrial Revolution begin before or after the time period shown on this graph? The Industrial Revolution began well before the time period shown on this graph. The Industrial Revolution started approximately in the 1800s. Our oldest graph up there was like 1880. I'm going to say it probably started around then, a bit before, when trains showed up. That was really part of the start of the Industrial Revolution. Ladies and gentlemen, it's just about the end of class. If you want to go, you can go. About how many parts per million of carbon dioxide were in the atmosphere in 1959? 1959, right about there. And you can say that's like 315 parts per million, ppm. right around 1959. So this is an exercise in reading the graph. 1975. 1975 is halfway between 1970 and 1980. You could say 330. 1985, 95, and 19. All right. 1985, halfway between 1980 and 1990. What's that look like? 345, halfway between 340 and 350. So that was 85, 95, halfway between 1990 and 2000, around here. Let's say 360 parts per million, 360 right there. And then 2019, that's probably the end of the graph right here. I think it's right here on that line, 410. So those are your numbers for this right here. Compare and contrast similarities, graph one above and graph 2. What's this? That's graph 2, graph 1. Okay. Similarities. Both graphs show an upward movement, very fast upward movement in carbon dioxide parts per million. Differences. Graph number 2 has every number above 300 parts per million. See, there's the 300. Here's the up. There's the up that we're seeing now. We wonder if it goes down, but it looks like it is going up some more because we see it's up here. We just took a look at a more current graph. It's no longer 400,000 years ago, it was down here. 100,000 years ago, it was down here. Now it's way up here. It's off the graph. It's that high now. Okay, and that's the differences. Graph 3 shows the temperature anomalies of Earth. This data was put together by paleoclimatologists, scientists who study past climates, using observations of ancient ice samples. Temperature anomaly is a measurement of how far off the temperature was from the average. Positive number means Earth was warmer than the average. Okay, this is the average. This is below average, colder. This is warmer, above. Surface temperatures anomalies before BCE, before the Christian event, before Christ, BC, Stone Age. Okay, did it ever get warmer? Yeah, right here, 400,000 years ago. And then, right there and right here. And yes, right there and right there. Okay, so up until the year 0, I see. So the 0 was not modern. This is the beginning. That was 2,000 years ago. So that's this. Okay, what time period is this graph? This is from 800,000 years ago to the birth of Christ, the year 0. So it was not, when I said the other one was to the present, the 0 means the year 0. So I was mistaken. Describe what happened to Earth's atmosphere during this time period. Were they stable? There was an increase over what looks like 100,000 years. There was a cycle. Remember the very first time we looked, we said there was a cycle 400,000 years ago. Goes down, then goes up, goes down, then goes up, goes down, then goes up, goes down, then goes up. It was supposed to go down again in here after the year 0, and 2,000 years later, it's up here. It's way up. All right.
So I am leaving, mister.
Okay, so that's pretty good. I will record some more for you later, and I'll send you that video also. Okay, so just a quick recap. Here's graph 3, and we want to take a look at what has happened here. And this is the surface temperature anomalies, and anomalies mean things that cannot be easily classified. So anomalies are values that are outside of the expected or expectations. So in this case, for temperature anomalies, we're talking about in degrees Celsius, and there's an anomaly of 0 degrees right here. There would be no change, nothing anomalous. But we have a chart here that goes back 800,000 years up to the year 0. BCE means before the Christian event or the birth of Christ. So that's the year 0. So if we look at a scale like this of 200,000 to there, this is 100,000 years. It's only been 2,000 years since the birth of Christ, roughly. That would be a space that's probably no wider, not even as wide as my crosshair cursor. So that would be out here, this short distance. And what has happened is the surface temperature has risen dramatically. We'll see that in another chart. So answer to question 10. I'm sure I've already done this, but we'll use it again. What time period does this graph include? This goes from 800,000 BCE through to the year 0 BCE. Question 11, describe what happened to Earth's temperatures during this time period. Were they stable? And the answer is no, the temperatures were not stable because we do have a record of anomalies. If they were stable, then they would generally stay the same and there would be no anomalies, no unclassifiable discrepancies or changes. So we can see over an 800,000 year history, the Earth's surface temperature has not really been stable. It has fluctuated, gone up and down over a range of -8 degrees to positive, let's say about +3, I think, +3 degrees. And this anomaly above 0, meaning an increase in surface temperature, below would be a lowering of the surface temperature. So there's the 0. This pattern of anomalies above an increase in temperature took place 400,000 years ago, then again about 300,000 years ago, then it drops down, and then about 250,000 years ago, there's this kind of double peak, and then 175,000 years ago, and then there was a drop, and the drop is an anomaly in the getting colder. So the surface temperature of the Earth got warmer and then got colder, warmer, colder, warmer, colder, warmer, all that kind of idea. Going up is warmer, going way up here is where it's above, it's a positive number. These are all negative numbers down here, but this is much more negative than that. Okay, so 150,000 years ago, and then around the time of the birth of Christ, we have a new beginning of a rise in the temperature. And of course, this is 2021 years ago. And we look like we're going through another cycle. The expectation would be either to have a little bit of an increase and then start to go down over the course of, what is that, something like 2,000 years. So it should be going down in theory, because none of these are really much wider than my cursor. And I'm saying that that's like 2,000 years. So it should be going down, but we'll find that it did not. So all of that is what's going on here. And were they stable? No, they were not stable, but they fluctuated within a range of -8 to +3 degrees, especially 400,000 years ago. Compare and contrast graph 1 and graph 3. Okay, graph 1 is this one, atmospheric carbon dioxide before the Christian event, and atmospheric carbon dioxide levels. Now, we have to note, this only goes back 400,000 years. They didn't put a negative sign on it here, up to the birth of Christ. So we need to compare this to half of graph 3. This is graph 1. What do we see? Atmospheric carbon dioxide levels go down and then up, then down and then up, then down and up and down, and then down, up and then down, and then up. So if we could pick this map up and place it on the other one, this is 400,000 years, we would go down to graph 3, and we would just look from here where 400,000 is, and we would try to see if there's a match between going up and then down, and then up and then down. So we could look and see how many peaks there are. 1, 2, 3 in the period 400,000 to 200,000. Are we going to see 3 peaks from 400,000 to 200,000? 1, 2, 3. Are they exactly the same? Don't know. We'd really have to look more closely. So under compare and contrast, similarities, they both go through a cycle of going up and then down and up and then down, up and then down. That's the similarities. Differences, this will be a little harder to think about other than, let's take a look. This is temperature anomalies, and the other is the carbon dioxide content anomalies. So literally, we'd really have to kind of put them on top of each other. So let's see if we can play with that for a moment. Now I can compare them. Temperature anomalies going up, and this is atmospheric carbon dioxide. When the carbon dioxide goes down to like 350,000 years, there's 350,000 years, the temperature anomalies seem to go down. And then there's the 300,000, and 300,000 is right here. So it's lower. It seems to me that we can actually draw a line kind of between, I know that's not straight, but that part and then this part goes there, and then I would say that this goes with that. There's a low and kind of a low. Maybe that's not a good line right there. Too bad I can't draw straight lines with this thing. But it looks like, it does not look like a peak here comes up with a peak there. And so we can argue that generally, when there are low atmospheric carbon dioxide levels, atmospheric carbon dioxide levels, parts per million, when there are low parts per million of carbon dioxide, there are low temperature anomalies. So I can write that right here and say it appears that when there are low atmospheric, yeah, all right. Low atmospheric carbon dioxide levels, there are also low levels of temperature anomalies. All right, and so this is going to be jam physics. Yes. Jam physics 03-26-21. All right, so that's basically what we can see from these two graphs. And of course, the other side is true. Higher carbon dioxide levels, higher anomalies in temperature changes. All right, so that's just a correlation right there for those two things. So that's good. Let's move on with what we were doing before. Go back here. So now that we've done that, we can actually compare and contrast, right? Differences. Not a lot of big differences other than we have earlier data, but I don't think there are a lot of differences personally. All right, graph 4 shows the average yearly surface temperature anomalies for Earth for more recent times. Okay, remember that a positive number means Earth was warmer than average that year. A negative number means Earth was cooler than average. So now we actually also talked about this in terms of Greenland, and we wanted to start looking at the most recent data here, 1992. What time period does this graph include? This graph 4 includes the time period from 1880 through to approximately 2010, a time span of 130 years. Over the time period that this graph covers, what is the general trend of the temperature? The general trend for the temperature is that the difference from the average has increased. If the average is 59 degrees, then the yearly surface temperature has been higher than 59 degrees as an average consistently from about 1975 through to 2010. All of these numbers, this part of the graph, all of these are anomalies that are above or an increase in temperature in degrees Fahrenheit. Here, earlier from 1880 through the rest of it, 1970, most of the trend has been a yearly surface temperature that has been below the average of 59 degrees, because these are all negative numbers. An increase here, generally 1930 to about 1945. What happened around here? This is World War II, right here, approximately 1939, 1935. War production, creation of more gas burning things, gearing up for planes, etc., etc. That's an anomaly that went about the period of the Second World War. First World War, Back here, 1914 to 1918, which would be in this period right here, you can see an increase, war production, I suppose, as well, but the amount, planes, there weren't that many planes. We weren't sending entire huge armadas of massively large B-1 bombers over the entire continent of Europe or over the ocean and then to Japan during World War I. We were doing all that kind of stuff here, and you can see a significant, consistent increase in temperature right towards the end. And right around 1945, we set off 2 atomic bombs. Lots and lots of photons released into the atmosphere, right about there, I bet. But more generally, the trend has been up and above, a change that's above the average. Okay. What time did we just talk about that? Over time period, what is the general trend of the temperature? I've just talked about that. Which general time period shown on this graph shows the highest temperature anomalies? The most recent from about 1975 to here, with a small significant blip for World War II. The Korean War right there. And what's here? Well, I don't know. I guess, you know, there are other things other than the Vietnam War. Compare the years 1960 to 2010 on this graph and the same year's graph 2. What are your observations? 1960 to 2010. With which one? Graph 2. 1960 to 2010. 1960 to 2010. Well, there you go. Atmospheric carbon dioxide has been steadily increasing. We talked about this earlier, Lorena, that in the general trend, it had never been above 300. And all of these numbers from 1960 through, I think this is 2019 right here, have been all the way up to 410. Let's go back to graph 4. Here's graph 4, 1960 through now. That's what we're looking at. I forgot. To 2010. Okay, 1960 to 2010 is from here. Yeah, to the end. Okay. We've seen a large increase in carbon dioxide levels, and we've seen a large increase in temperature anomalies, both going up. Both going up. Similar to what we saw for our Jamboard picture for the last 400,000 years. Low carbon dioxide, low temperature anomalies. High carbon dioxide, high temperature anomalies. So that idea continues here, and it's more prevalent. We can see it because we're tracking more of the data more closely. Okay, so we just talked about that. All right, graph 5 shows the amount of ice loss measured in gross tonnage. We talked about that. Gross tonnage. Okay, that's just straight up tons. Here's the Greenland ice mass, and we talked a little bit about that already. But you can see this is from 1992 to 2012. Gross tons of ice lost off of Greenland. And this is cumulative. Okay, so there was basically no real loss, or they didn't have records. Very little loss in 1992, but the amount of loss has gone up. And so for the last 20 years, we have lost a total of, about 3,000 tons. 3,000 tons of ice, and a ton is 2,000 pounds of ice. So 3,000 tons, 3,000 times 2,000 is 6 million pounds of ice. What time period does this graph include? From 1991 through to 2012. What is the overall trend of the amount of ice in Greenland's ice sheets? The overall trend is that it has been losing more and more, and the cumulative is, just as I said, 3,000 tons or 6 million pounds. Make a connection between graph 4 and graph 5. There's graph 4. Well, we did that. We started to look at this right here, Lorena, and we could only look from this part from 1990, which I guess is at a peak here, but we can see that the temperature has been the highest. The temperature anomalies, each year it's been about a half a degree or a full degree, maybe almost a 1.5 degrees above the average consistently each year. And so from 1990 to 2010, all of this is going up. And what we see here for the same period is that the ice is melting. That's what's happening. More and more of it is melting as we see that more and more years of above average temperature. Why do they appear to show the same trend? Because we just talked about that. All right, graph 6 displays changes in sea level. We also talked about this, and I started to look at that with the meter stick. Sea level changes. So sea level changes for the period of about 1990. Right here, we can see that it has gone up, and we talked about that in 30 years from 1990 to about 2020. For those years, it has gone up, and it looked like approximately 3 inches, because it's what about 250 millimeters. 200. We went from a difference of 1990 was right here about 150 to say 225. So that's what time does this graph include? 1880 through 2020. Okay. About how many millimeters did the sea level rise from 1900 to 2000? So from 1900 to 2000, it was at about, we'll call that 25 millimeters above, to 2000, which is here, 25 to 175. So that was a rise of 150 millimeters. So for that period of time, 150 millimeters. And we're going to stop that for a second. 150 millimeters. If I can bring this into focus. There we go. 150 millimeters is here. That's 150 millimeters because each centimeter is 10 millimeters. So that over the course of 1900 to, that's 100 years, we've had a rise of about 6 inches. So from 1900 to 2000, 100 years, it's about, what did we just say? 6 inches, 150 millimeters or 15 centimeters. Describe the overall trend of the sea level. The seas are getting deeper. The level of the sea is rising. Make a correlation between graph 5 and graph 6. Here's graph 6. Graph 5, I think, is Greenland. Yes, there's graph 5. 1990, okay, 1992 to 2012. The amount of ice that's lost, and where is it lost? It goes into the sea. So from 1992 to 2012, if we can look at that. From 1992, that's going to be to 2012. That's going to be this segment right here. from about here to, yeah, about there, 1992 to 2012. It has gone up consistently, and here is 1992, that'll be about there. We could say it's at about 150, and then it went up to about 225, so that's 75 in 20 years. 1992 to 2012 is 20 years. They have the same trend because the ice that is melting off of the Greenland sheet is going into the ocean. Since that ice is turned into water and is in the ocean, we can track right here the sea level change. And this is not just Greenland's ice sheet, but it is including Greenland's ice sheet. Okay. All right, part 3, claim, evidence, reasoning grid. Do carbon dioxide levels in the atmosphere and Earth's temperature appear to be related? Yes, they do. The evidence is in the tape that I'm going to make for you of all of this, and we talked about that. My reasoning, that's your reasoning, but you can go over the tape. How does the carbon dioxide level in the atmosphere now compare to the carbon dioxide levels in Earth's history? Way above the historic maximum. That's where I was talking about. It had never gone above 300 parts per million, and now everything is above 300 parts per million, all the way to 400 parts per million. That's what goes in here. That's the evidence from the graphs. Does the increase in global temperatures during recent decades appear to be impacting factors on Earth's surface? Yes. The increase in the temperatures is melting the Greenland ice sheet. What's the evidence? We could see that since 1992, Greenland has lost 3,000 gross tons of ice into the ocean. And that's the end of all of this. So I hope this works, Lorena. I'm going to put this all together and edit it, and I look forward to hearing your feedback. Thanks.